The next example is the one that follows next. And you look at that example, and we have this example that asks how many users can be supported by 0.5% blocking probability for the following number of trunk channels in a blocked call cleared system. So when you hear of blocked call cleared system, you understand whether Erlang A, B or C. So what we need, we can use either table 1 or we can use the graph that we have seen on figure 8. If you are very ambitious, you can apply the Erlang B formula as it is without using the graph. That will still give you the answer if you have a programmable calculator. Then what we know is that we are given that C is 1. Oh, of course, we are saying for C is 1, C is 5, C is 10, 20 and 100. We don't want to do all of them. We just need to do one or two. So for the first one, C is 1, and we are told that we are told that each user generates 0.1 elams of traffic. So that means that AU is equal to 0.1. Okay, so you are saying that we have one channel, 5, 10, 20 or 100, and we are told that each user generates AU equals to 0.1. The GOS is 0.05 or 005. That is the one that we are given, and we are using the relation A is equals to the traffic offered is equals to the number of users times the traffic offered by each user. That will give you A. That says that the number of users therefore that can be supported is equals to 0.1 divided by 0.1 is equals to 1 user. Moving on, we see that if we have the question that was asking what? How many users can be supported? So we are supposed to go to table 1. That is the part that I missed. Go to table 1 and look for GOS is equals to 0.5. We are talking about GOS of, that is the second column that we want to use, and the number of channels available is 1. So if you don't have that one, then we can go directly to the figure 8. Figure 8 is right here. One channel is right there. Now that is where we have one channel, the very top left, and the GOS is where? Right there. So what does that tell you? It is simply giving us 0.1 capacity at the bottom. You can see that. I repeat that there is 0.1 here. It's meeting 0.5 at that point, and when you go down along that line, it gives you 0.1 capacity. Now that we have got, this is the one there, one that we have got as A, which is the traffic intensity in Erlang. Once we have got that, then we go back to our question, and we know that A is now equals to 0.1. AAU is equals to 0.1. Therefore, the number of users that can be supported by one channel is how many users? Does that make sense? Because we say that one channel can support one user. Yes, we are saying that in an ideal system, one user is supported by one channel. So that's actually a proof or verify. You cannot have one channel that is supporting more than one user unless you have a very high blocking probability that when you want to support two users, one of them is a block, and that is acceptable to your system. So first of all, we proceed by agreeing that is correct. We move on, and we want to say now that we want now to consider when C is equals to 5. Our GOS is still 0.005. So we go back to our graph, which is on figure 8. Don't confuse those two graphs. We are saying that C is 5, the one that I have circled, and the rate of service is still 0.05. So the curve for 5 is one that I have added a blue line. So where are they meeting with 0.5? At that point. And therefore you go down to seeing that your traffic intensity A is approximately 1 point what? You know this is a 2, this is a 1, therefore this must be 1.2 or 1.3 there. So let's see if that is correct. Yes, so we are seeing that from our figure, the estimate is 1.13. So if you give me 1.1, that is fine. If you give me 1.2, that is fine. We give an allowance of plus or minus 0.1. That is acceptable. This is 1.1, this is 1.2. Okay, then we can do number 3 as the last one. Let us try to look at number 3 as the last one. We know we have CS10 and GOS is 0.05. We come back here and we say that this is our GOS, this is our 10. So we follow this until this point, then we drop directly. I have done it not very well, so I can draw it slightly better. Right there. So this is a 1, 2, 3, 4, 5. So that is a 5. Then we are between 5 and 6. So if we say that is about 5.3 something, or 5, then it would not be very long. That would be our A. And if we go back now to our illustration, did I get something wrong? Let's go back. Saying about 4. I used the wrong table. I used the wrong figure. That is how bad things can get. So we come back. 10 is right there. Our GOS is there. The graph of 10 is following there here, and therefore you stop at this point. The one that I have dotted. So when you go down, this is actually a 4, because you can see this is 1, 2, 3, and 4. So when you say that your A is approximately 4, you are right. But the person who had got this answer got as 3.96. This is within the acceptable range of 3.9. The range of 3.9, you said we allow 0.1. So if you give 3.9 or 4.0, you are within acceptable range. That is it. All you need to know about graph number 9. You can do the rest. And that is the end of that lecture. We should now start on the new section. Example 2 is right there. You can look at it and look at those examples. Example 3, of course, and the solutions are there. Example 4. Hey, this example 4 is important. Let me see if this is quite an important example that we need to look at. So let us look at this example very quickly. This employs the Erlang C formula or the Erlang C chart. So let us look at this one. This says that a hexagonal cell with a 4-cell system has a radius of 1.387 kilometers. A total of 60 channels are used within the entire system. If the load per user, this is what we call AU, isn't it? A small u. 60 channels are available. This is C. Area or radius is not A. This is our N, I believe. This is lambda is already given. 1 call per hour. This is called arrival rate. Arrival rate. Compute the following for an Erlang C system that has 5% probability of delayed call. So the first question is asking how many users per square kilometer will this system support? What is the probability that a delayed call will have to wait for more than 10 seconds? These I believe are the questions that we need to address. Or the last one is asking what is the probability that a call will be delayed for more than 10 seconds. Very important question. One is more than 10 seconds. The other one is what is the probability that we have to wait for more than 10 seconds? Let's get that correctly. Will be delayed for more than. So we have waiting for more than 10 seconds and being delayed for more than 10 seconds. Okay. Now that the solution is here, let us just look at it. We are given that the cell radius is 1.387 kilometer. Therefore, to calculate the area of a hexagon, the formula there that you apply that says that the area of a hexagon is given by 2.598 times r squared. That should not be something new. That comes from mathematics. When you do that, you get that the area of that square kilometer that cell is 5 square kilometers. Then the number of cells in one cluster is 4. This is what we said was n. C is 6. Therefore, this is the total number of channels available for the entire cluster. That is what we are told. So per cell, you do 6 divided by 4. You get 15 channels available per cell. So from the Erlang C chart, you look at 5% probability for C is equals to 15. Let's see that. Erlang C chart. Erlang C chart is this one. So we know that we have C is 15 at the very top and we have 5% probability of delay. So we just follow the curve where they meet. They meet at the point that I am putting a dot. So when you go down from that point, it shows that this is 5. 5 is supposed to be where? This is a 1, this is a 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are between 9 and 10. We are closer to 9 than we are closer to 10. So anything between 9 to 10 for that should be fine. So let's see if we get anything between 9 and 10 from our example. Yes, you see it is actually saying that the capacity A is 9 because it looks like it is sketching at exactly where the line of 9 is. So having seen that, then we can say that the number of users is obtained from this formula that says A is equals to U times AU, isn't it? So we need U divided by AU divided by AU. We are saying that U is equals to A over, we are given that AU is equals to what? We are given that AU is 0.029 and we have found that our A is 9 and therefore we can say that the number of users that can be supported by that system is 300 and what? We have answered the first question that was asking the number of users per, that is the number of users per cell. So then we need to calculate per square kilometer. So of course we say 310 divided by 5 and we get 62 users per square kilometer. The other question is asking what? It's asking what is the probability that a core will will be delayed for more than 10 seconds. Are we told that the GOS is for a delayed call, but now we want for more than 10 seconds. Let's see how we do that. We are given that the call holding time is 1. Not that. We are given that the call arrival rate is 1. That we are given, right? But the call holding time is the one that we need to calculate. And we can say that call holding time is going to be given by, I think we had this formula that was saying that AU is equals to A times H. We are saying that AU is equals to lambda H. And we want H. So we say H is equals to AU divided by lambda. We know that AU is 0.29. What we are given is the load per user, which is 0.029 Erlangs. This was Erlangs per what? Per hour. Is that the case? Of course, Erlang. It is Erlangs without per hour. Then we say that the lambda here is equals to 1 call hour, 1 call per hour. So what that gives us is that when you say 0.29 divide by this 1 call per hour goes on at the top. And therefore you have 0.029 hour. That is the call holding time, the average call holding time per user. So you convert that to seconds, you get 104 seconds, 0.4 seconds. The probability that a call will have to wait for more than 10 seconds is obtained. That is the probability that calls are delayed for more than 10 seconds is given by this one. This is not the ratio of all the calls. This is the ratio of only the calls that are delayed. So when you are unlucky to be delayed, the probability of delay is bigger than being 10 is 56.29%. That means that more than half of the calls that are delayed more than 10% or 10 seconds. Now the other question is asking the probability that a call will be delayed for more than 10 seconds. Now that is a general call. A call that you are out of the blue. This is why we are saying we had 100 people calling. 5% of them are delayed, okay, with some delay. So we want to find the probability that a general call will be delayed. So we are saying that we take this 5%, you multiply by the delay of bigger than 10%. That is the one that will give us that a general call is delayed for more than 10 seconds. That is what we say we get here. That is what you say 0.05 multiplied by what we have found earlier, and you get that generally a call that is delayed, it takes more than 10 seconds is equals to 2.8%. That's a very significant example.